Hello, welcome to lecture 24 of the course. In the last lecture, we have started discussing about superconducting circuits. We learned that how one can realize a superconducting qubit or superconducting two-state system by bringing two superconductors adjacent to one another. We will continue our discussion on superconducting circuits in this lecture as well. So, let's begin. In the last class, we have discussed briefly about some properties of superconductor. There we learned that in a superconductor, the charge carriers are the so-called Cooper pairs, and these Cooper pairs are formed by two electrons coupled to each other via the phonon interaction. Because these two electrons are glued to each other, so there requires some amount of energy to break it, and this result in the so-called band gap, and this band gap is denoted by the symbol twice delta. Now, as per this the so-called BCS theory, the band gap at the absolute zero temperature T is equal to 0, and the critical temperature of the superconductor is related by this expression. And we also learned, and it is obvious, that the particle number can change in a superconductor by twice n, where n is the number of electrons. And we also learned in the case of a superconductor, and we discuss it in the context of superconducting ring, that the magnetic flux is quantized, and magnetic flux is an integral multiple of the so-called flux quantum phi 0. Then we went on to discuss the so-called Cooper pair box. A Cooper pair box is formed by two superconductors placed close to one another, and the separation between these two superconductors are on the order of nanometer, and a typical size of the whole Cooper pair box is in the micrometer range. We went on to discuss the Hamiltonian for this Cooper pair box, and it has two parts. One is the charging part and another one is the tunneling part. And this Hamiltonian we can rewrite using the number operator, where charge operator is defined in terms of the number operator as q cap is equal to twice of the QE is the charge of the electron, and n cap is the number operator, and the other parameter Qj, which is the gate charge, is defined in terms of the parameter Nz. Using this Hamiltonian can be written, and we have shown that in the last class and analyze it, assuming that this Josephson energy Ej is much weak compared to the charging energy Ec, and then we get this typical plot. And this plot clearly shows that because of the presence of this Josephson energy crossing is avoided, resulting in the phenomena of avoided crossing. And next we discussed how this Cooper pair box can be realized as a two-state system, and that can be done if we focus ourselves around Nz is equal to say 1/2, which means that if you tune the Cooper pair box by appropriate gate voltage such that the parameter Nz is around 1/2, and then we can realize it as a two-level system, and we get this Hamiltonian. This Hamiltonian was also analyzed in detail, and we get this typical plot here. From this plot, as you can see, that the energy, there are two energy levels, and these two energy levels are separated from each other by Ej. Ej is the, as I said, it is the Josephson energy. Now, after having the qubit, the next obvious question is how to manipulate this qubit, and what kind of radiation is needed to couple the ground and the excited state of the qubit. Let us make a quick calculation. You know, in this superconductor, these superconductors are generally made up of aluminum materials, and in a aluminum, the critical temperature for the aluminum is on the order of, that means the Tc is on the order of 1 Kelvin. So if you want to have a very effective superconductor, the operating temperature is kept much below the critical temperature, and this is kept around 20 millikelvin. 20 millikelvin means the thermal energy kBT is on the order of, if you put the number and kB is the Boltzmann constant, this is going to give you around 2 micro electron volt. So this has a clear significance. I'm coming to that soon. Now, what about the charging energy? The charging energy is QE square by 2C, and in the Cooper pair box made up of aluminum, this charging energy is around 100 micro electron volt. Okay, and in terms of temperature, we can write ECH as 1 micro electron volt, that means 100 into 10 to the power minus 6 electron volt, and 1 electron volt is around 10,000 Kelvin. So in terms of Kelvin, the charging energy is going to be around 1 Kelvin, as you can see. All right, so now the ground state and the excited state are separated by the Josephson energy EJ, and this separation, if you really want to have a quantum system, this separation must be greater than the thermal energy, which is around 2 micro electron volt in the case of this aluminum Cooper pair box. So therefore, in this typical Cooper pair box made up of aluminum, this Josephson energy is kept around 20 micro electron volt, which is much larger than the thermal energy 2 micro electron volt. Okay, also you see that because EC is around 100 micro electron volt, EC is greater than EJ, and obviously the Josephson energy is smaller, which is what is required, right? So if you want to couple the ground state and the excited state, you need to send a radiation which is going to have an energy on the order of EJ, and that means you must have h bar omega, where omega is the frequency of this radiation. It has to be equal to, h bar omega should be equal to EJ, and in our case EJ is around 20 micro electron volt. If you put the numbers, you are going to get omega is equal to 2 pi into 5 gigahertz. Now I hope you know that gigahertz, 1 gigahertz is equivalent to, in wavelength, it is equivalent to 30 centimeter. So quite clearly we are in the microwave regime now. So that means if you want to couple the two energy levels, then you have to send a microwave signal. Now in this context, let me make few comments about atom field interaction in cavity QED. So you know that if you have an atom and if you want to have interaction with the electric field, then you are going to send a signal to the atom, but this kind of interaction is not going to be effective because this interaction is going to be very, very small. So what is done in cavity QED, what is done is that you place this atom in a cavity, the so-called Fabry-Perot cavity, and if this atom is placed in this cavity, the optical field inside the cavity can bounce back and forth between these two mirrors for good amount of time, depending on the quality factor Q. Don't get confused with the charge. This is Q is the quality factor. Say quality factor is say 10 to the power 4 or 10 to the power 5. Say 10 to the power 4, that means 10,000. This means that the photon can bounce back and forth inside the cavity for 10,000 times, and this way this field is going to interact with the atom quite strongly. In the case of a superconducting qubit also, we need an appropriate resonator operating in the microwave frequency so that strong field qubit interaction can be achieved. This is achieved by the so-called transmission line resonator. You may know that microwaves can propagate through a transmission line. Now here in this figure, I am showing you a typical microwave transmission line resonator, and this figure is taken from the journal Physical Review A, volume 69, page number 062320. This was published in the year 2004 and it's a landmark paper in circuit QED. And I encourage all of you to go through this paper. Now here it is shown that this resonator is formed by cutting the transmission line in two ends here, in two parts here. So here this is the transmission line This is a transmission line. Let me denote it as TL. And this is also a transmission line. This transmission line is generally, the length of the transmission line is around in centimeters, as you can see from this figure is in centimeter. And the distance between this transmission line, actually this is no longer a transmission line, the middle one, this is transmission line resonator, because the transmission line is now cut into two parts, thereby forming the transmission line resonator. And you can see the Cooper pair box here in green here. This is the Cooper pair box, and this is placed at the antinode of the electric field so that there is strong interaction. Again, here also you see the Cooper pair size is on the order of 1 micrometer, as you can see here. And below this figure here, this is a representation of this circuit in the lump circuit representation. C0 is the capacitance of the coupling capacitor to the measurement electronics, and CG here is the capacitance of the coupling capacitor to the Cooper pair box. And this is why this kind of setup is, because you see a lot of electronics and this capacitance, inductor and this kind of stuff are involved here. This is why this kind of setup is termed as circuit quantum electrodynamics. Quantum because you are dealing with a Cooper pair box. Now let me talk briefly about transmission line, as it may help you to give more clearer understanding. What is a transmission line? To be put very simply, a transmission line is a set of two parallel metallic wire placed close to one another. These two metallic wire are adjacent to each other, and in this metallic wire, in this structure, a microwave signal can propagate. Okay, one can actually have a circuit model of this transmission line, and in the limit of sufficiently long wavelength and small frequency, this circuit model works pretty exactly. To understand this circuit model, let us consider two parallel metallic wire once again here, and let us say by some means we are able to create surplus of positive surges in the upper wire and surplus of negative surges in the lower wire, and that say covers a distance of say A. And this is what we also seen how we have done that in the case of the Cooper pair box. When the Cooper pair tunnel from the upper island to the lower island, then the upper island is going to have positive surge and the lower island is going to have negative surge. Similar kind of situation is here also, and as you can see here, this is going to result in the electric field distribution between these two metallic wires, just like in the case of a capacitor. Okay, now you have many such unit cells of length A, right, like this as is shown in this diagram, and we can therefore represent this structure as a set of capacitor. For example, this one, this one I can represent it by a capacitor like this, say having capacitance C, and again this structure, this unit cell having length A, this unit cell I can represent it by a capacitor C, and then the next one, and so on. We can go on and represent every unit cell like this kind of a capacitor. But there is also the issue of current flowing in the structure, and these currents generate magnetic field, and the magnetic field again create electric fields and so on. And all these features can be incorporated to the model by joining these nodes. Okay, you can join these nodes by an effective inductance, say L. All these features can be captured if I join these nodes by inductance. Similarly for here you are going to have inductance, effective inductance L. Why I am saying effective inductance? Because I can by convention, without loss of any generality, lower nodes I can actually join this by simply a line, and this is our circuit model. Now in this structure, if it is cooled to very low temperature, you need not have to take into account the loss. Thereby you can avoid putting resistance into the model, and this is so in the case of the transmission line model of superconductors. Now, using elementary circuit analysis, it can be shown that the wave propagating through this transmission line has a constant velocity. Let me very quickly take you through the analysis. So we have this model here, this circuit model. There are many nodes here. In the nth node, let's say the charge is here Qn. Okay, the charge here in the nth node is Qn, and in this node the charge is Qn minus 1, and then you have in n plus 1th node the charge is Qn plus 1. Current In is flowing from the node n minus 1 to n. This current is flowing, and similarly current In plus 1 is flowing towards this node n plus 1th node, and this is going to help you the set up a equation for charge conservation because charge is flowing. So Q dot is equal to In minus In plus 1, because in the nth node current is going into the nth node and In plus 1 current is going out. That's the reason we are having a minus sign here. And again there is a voltage drop between the nth node and the Qn plus and n minus 1th node, and this voltage drop can be expressed by this equation, right? This is the familiar equation, all of you are familiar. Voltage is equal to L di dt. Now if we decrease this length A, if A tends to 0, then we will go into the continuum domain, and in the continuum domain we are going to have a current like this. And as you can see, suppose in the nth point, which is distance x is equal to na, the current In, I can write it as I at x is equal to na, and this continuum equation I can write in the limit when a tends to 0, say I can write In plus 1 minus In is equal to a di dx delta I delta x. Similarly, for the time rate of change of the charge, I can write it as this equation, del q del t is equal to minus a del I del x. So again from the voltage drop equation I can write this equation in this form. Now you see, because just be careful that when I am writing this equation here In plus 1 is there, right? So that's the reason here plus a is there. Now here I have the opposite Qn minus 1, so that's the reason minus sign is there. I hope you are getting it. So using this equation which we have got from the voltage drop equation, and this equation which we have got from the charge conservation, using these two equations one can easily obtain this second order differential equation for the current. And I will urge you to get this equation. It's very simple and straightforward. Please try to do that, otherwise we are going to do in the problem solving session. Now this equation I can rewrite in this particular form, where the small l is the inductance per unit length of the unit cell, and small c is the capacitance per unit length of the unit cell. And this you can see if we compare with the classical wave equation. The classical wave equation goes like this. If you remember, delta to f delta x square is equal to 1 minus v square delta to f delta t square. If you compare this equation with this classical wave equation, you can immediately make out that the velocity square is equal to 1 by lc, and therefore velocity is simply 1 by square root of lc. So now because this small l small c, this product is simply a constant quantity, it's characteristics of the material only, so v is constant, v0 is constant, and that's the reason we say that wave, now here the current is propagating through this transmission line as a wave, current wave. Similar equation actually you can obtain for the voltages as well. So either the voltage or the current, you can have a voltage signal or you can have a current signal, and that can propagate through this transmission line with a constant velocity. So this circuit model as I have already told you, work perfectly if we consider sufficiently long wavelength, and that's the regime where microwave, microwave has a long wavelength in the range of gigahertz, and as I said earlier, 1 gigahertz is around 30 centimeter. Okay, and it works in the small frequency domain. Now, as you can see from this transmission line model, one unit cell of the transmission line in the circuit model consists of a capacitor C and an inductance L. So basically it's a LC circuit. So one unit cell of the transmission line is going to be represented by a capacitance C and inductance L. And if we consider very low temperature, you need not have to bother about resistance. Now the question is that what happens if we go to the quantum regime? So that means now we have to do the quantization of this LC circuit. So let us do that. LC oscillator is the building block of a transmission line. Let's say we have this LC circuit. Here is the capacitor having capacitance C, and we have a inductor with inductance L. The upper plate of this capacitor has a positive charge, and this positive charge is denoted by Q, and because of the flow of this positive charge, there is a current through the inductor, and the current is flowing along this direction, let's say. Now you know from your elementary physics that the energy of the LC oscillator can be written as this expression. By this expression, the energy in the capacitor is Q square by 2C, or half CV square, where V is the voltage, or in terms of charge and capacitance, we can just write Q square by 2C. This is the energy stored in the capacitor. And then in the inductor, the magnetic energy stored in the inductor is half Li square. This we know from our basic physics. Now this expression can be written in terms of the magnetic flux as well, because you know that the magnetic flux phi is equal to inductance into the current. Using this energy expression for this ideal LC oscillator, ideal because we are not considering any loss, there is no resistance, so we are going to have this energy expression Q square by 2C plus phi square, that's the phi is the magnetic flux, phi square by 2L. So as you can see, this energy in this energy expression, it is quadratic in charge and quadratic in the magnetic flux. If we now make an analogy of this energy expression with the Hamiltonian of a linear harmonic oscillator, that is a mass m attached to a spring constant k, and this mass is displaced from the equilibrium position by a distance x, and k is equal to m omega square, then we know this Hamiltonian can be written for this linear harmonic oscillator p square by twice m plus 1/2 m omega square x square. Now if you make the analogy such that the charge q is analogous to the momentum p, the magnetic flux is analogous to the coordinate x, then this capacitance C is analogous to mass m, and 1 by L. Please do it yourself also and see this little bit carefully. If I make the analogy of 1 by L to m omega square, then I can write the Hamiltonian for this LC circuit, classical LC circuit I would say, would be given by Q square by, because the Hamiltonian refers to the energy, Q square by 2C plus phi square by 2L. In fact, this analogy makes sense because you know from this analogy we can immediately have that omega square is equal to 1 by LC, that means omega is equal to 1 by square root of LC, which is the resonance frequency of an ideal LC oscillator. Now to go over to the quantum regime, we have to impose the commutation relation, and in fact what we are going to do, we are going to consider the charge Q and the magnetic flux phi as the canonically conjugate variable. Then if I go to the quantum regime, in the quantum regime this canonical conjugate variable can be replaced by their corresponding operators. So I am going to replace Q by Q cap and the magnetic flux phi by the magnetic flux operator phi cap, and then I am going to impose this commutation relation phi cap Q cap is equal to I h bar. Just recall that when quantizing a linear harmonic oscillator, we impose this commutation relation. So we are actually doing here everything in the analogous way to that of a linear harmonic oscillator, the canonical quantization procedure that we are adopting here. And if we do that, then I can write the Hamiltonian for the LC oscillator. The quantized LC oscillator can be written as Q square by 2C plus phi square. Now everything is in quantum mechanical operator. Phi is the magnetic flux operator. So this is the Hamiltonian I have. I can write this also in this form, Q square by 2C plus 1/2 capital C, which is analogous to mass, omega square phi square, and yeah, this is what I have, phi cap square, that's the magnetic flux. So this is now our quantized Hamiltonian, the Hamiltonian for the quantized LC circuit. Let us now define, similar to the case as we do for the usual linear harmonic oscillator. Again, you recall, in the case of the linear harmonic oscillator, we write the position operator like this in terms of annihilation and creation operator, XZPF, where XZPF is the 0-point fluctuation of position, A or the coordinate A plus A dagger, and the momentum operator we write it as I m omega x 0-point fluctuation A dagger minus A, or this also I can write it as I PZF, that is the fluctuation in the momentum, 0-point fluctuation in the momentum. This is what we can write for the case of a linear harmonic oscillator. In the similar way, I can now write phi, which is acting like a coordinate here. I can define phi is equal to phi ZPF, that is the 0-point fluctuation in the magnetic flux. That would be A plus A dagger. And by the way, phi ZPF is equal to, just like here, XZPF, the 0-point fluctuation for the linear harmonic oscillator is h cross divided by twice m omega under root. In the similar way, here phi ZPF, the 0-point fluctuation in the magnetic flux, is going to be given by twice c omega under root. Now you see, omega is equal to 1 by root over LC here, and using this I can write phi ZPF is equal to h cross divided by 2. If I put omega here, I would have here under root here, and I have here root over LC, okay, and divided by C. This I can write as under root h cross by 2. I can write it as L divided by C under root, and this quantity, square root of L by C, is the so-called characteristic impedance Z. Z is the characteristic impedance of the LC circuit, and it's a very important parameter, characteristic impedance. Therefore, in terms of the characteristic impedance, phi ZPF is equal to h cross by 2 into the characteristic impedance. Then I have to take the square root. So this is the 0 point fluctuation of the magnetic flux. So what I have, that magnetic flux operator is phi ZPF A plus A dagger, and similarly the charge I can now write it as I into L into omega, okay, actually C, right, because mass is analogous to capacitance C, and I have here phi ZPF, and I have here A dagger minus A, and this also I can write it as I 0 point fluctuation of the charge A dagger minus A. In fact, you can show that QZPF, the 0 point fluctuation in charge, is going to be given by this expression, square root of h cross divided by twice z, where z is the characteristic impedance of the LC circuit. So let me write it once again. The magnetic flux operator in terms of the creation and annihilation operator is simply phi ZPF A plus A dagger, and charge operator Q is equal to I, let me write it, 0 point fluctuation of the charge A dagger minus A. So with these things I can immediately now write my Hamiltonian in the usual form. H is equal to h cross omega A dagger A plus half. So this is the usual looking Hamiltonian for a harmonic oscillator, and this is what we are writing for the quantized LC oscillator. So as you can see, the when quantization is done, the LC oscillator also behave like a harmonic oscillator. However, here omega is equal to 1 divided by square root of LC, and annihilation operator is defined as, you can work it out easily. You can show that annihilation operator is 2 into phi ZPF, and here you are going to have magnetic flux plus IZQ charge operator, and the creation operator A dagger is equal to 1 divided by twice phi ZPF, okay, and you have here phi cap minus IZQ. Okay, so you see that when quantized, each unit of the transmission line behaves like a simple harmonic oscillator as per our circuit model. This implies that to excite a unit cell in the transmission line, the microwave that is incident on the transmission line should have energy that is equal to the resonant frequency of the LC oscillator. And you know that when quantized, microwave, which is an electromagnetic radiation, as we have already done the quantization of electromagnetic radiation, we see that even in the case of the microwave, each of its mode must behave like a harmonic oscillator. Now, as I have already shown you that each unit of the transmission line is a harmonic oscillator, so we can actually write down the Hamiltonian for a transmission line, a quantized transmission line, without going into any details. Let me write it. The Hamiltonian for transmission line, Hamiltonian for transmission line is going to be, it's going to be a set of harmonic oscillator, and total Hamiltonian would be sum over k h cross omega k A dagger k a k plus 1/2. So this is the Hamiltonian for the transmission line. Now if we talk about the transmission line resonator, a transmission line resonator, as we have discussed earlier, that it is formed by cutting a transmission line at two ends, then you get the so-called transmission line resonator, and this should actually remind you about the so-called standing wave that we have also discussed earlier. So clearly this transmission line resonator, here the microwave is going to form a standing wave, and when quantized we have seen that this standing wave mode also behaves like a harmonic oscillator. So for the case of the transmission line resonator also we can write down the Hamiltonian, and this Hamiltonian is going to be again a harmonic oscillator. So we can write it in this particular form, say S cross omega n a n dagger a n plus 1/2. So when quantized, this transmission line resonator Hamiltonian is going to be of this type. Now you also saw earlier that in the case of a transmission line, the signal that propagates through the transmission line is due to the voltage wave or a current wave. Now the voltage being a quantum quantity, when we are considering a quantized transmission line resonator, it is expressed in terms of certain annihilation and creation operator for a single unit cell. This voltage is going to be an operator, and that is nothing but the rate of change of the magnetic flux operator, phi dot. Rate of change of magnetic flux gives you the voltage. So we have already the expression for phi, so thereby you can show that this is going to be simply I omega phi ZPF a dagger minus a. Okay, so this is going to be the voltage operator. Now the question is, for the case of the transmission line, this is for a single mode. For the case of a transmission line, the voltage operator is going to be V of x is equal to phi dot x. Okay, this is going to be sum over n, because there are many modes are there. This is I have written for a single mode. This I am writing it for many modes. That is going to be I omega n phi 0-point fluctuation of the magnetic flux, then annihilation creation operator of the nth mode, and annihilation operator of the nth mode here. Actually many times what happens is that just to maintain the hermitativity and for convenience, we can write this part simply by an dagger plus an. This is more convenient for many purposes. So we are going to write the voltage operator for the transmission line resonator as sum over n omega n phi ZPF an plus an dagger. Okay, by the way, this is basically can be obtained by using unitary transformation. It's not going to change any physics at all. Now the Cooper pair, or for that matter any superconducting qubit, interacts with the microwave in the resonator via this voltage. Let us understand how coupling of the voltage to the Cooper pair box happens. Now let me remind you about this particular diagram that I have shown you earlier. Here as you can see, this green box which is the Cooper pair box, this is getting coupled to the microwave via the voltage or the current signal. And to understand it, how this is happening, let us consider that the gate charge QG in the Cooper pair is getting changed due to the quantum fluctuation, quantum mechanical voltage fluctuation by say delta QG, and this part is the quantum fluctuation in the voltage. Okay, then the charging part of the Cooper pair box Hamiltonian is going to be, you have the charging energy expression, you remember, then in that expression you just have to change this QG by delta QG. Again, this delta QG is the change in the gate voltage due to the quantum mechanical fluctuation in the voltage. And this, if I expand, before I expand it, let me also tell you that this delta QJ quantum mechanical fluctuation in terms of the gate voltage is V This is the voltage operator, and Cg is the capacitance of the coupling capacitor to the Cooper pair box. In fact, here in this diagram you see Cg is this one. So if I expand it, this particular term here, then I'm going to get terms like this. We are going to have term Q minus Qg whole square divided by 2c minus Q minus Qg into delta Qg divided by C plus delta Qg whole square divided by 2c. Now this quantum fluctuation is very small, so therefore this particular term can be neglected. This is very small, so we can neglect it. And if you look at this particular term here, the voltage is entering into the Hamiltonian when we have expanded it, so we can easily make out that this is basically the interaction part of the Hamiltonian. So we can define interaction Hamiltonian. Let me denote it by HINT, and this part is simply 1 by C minus 1 by C Q minus Qg. This refers to the atom or the two-state system or the superconducting qubit, and this part is coming from the quantum mechanical fluctuation in the voltage, and therefore this is the coupling term. And now I can in terms of the voltage I can write this HINT interaction term we can write, and this is going to be minus Cg divided by C Q cap minus Qg into the voltage operator. If we focus only on the field mode, then I can write HINT is equal to minus Cg by C. If I just focus on one single mode of the microwave or the field, then I can write this potential, this voltage operator, as omega phi ZPF, that is the fluctuation in the magnetic flux, quantum mechanical 0-point fluctuation in the magnetic flux, and A plus A dagger. Okay. Now I can write it in terms of the number operator also. If I take Q minus Qg is equal to twice QE n minus nz, then I can write my interaction Hamiltonian HINT as minus Cg by C twice QE 0-point fluctuation in the magnetic flux into omega n minus nz and A plus A dagger. Now, in order to obtain a two-level quantum system out of this Cooper pair box, we need to focus around Nz is equal to 1/2, and we have already had a discussion about this issue earlier, and you are pretty familiar with this particular plot. So if we focus around Nz is equal to 1/2, then we can have a two-level quantum system where the upper energy state can be considered as, say, QED-E, and this is what your QED-E, this is the excited state, and the lower one is the ground state. So we have effectively a two-level system, ground state energy QED-Z and the excited energy state QED-E. And taking this as our basis state, QED-Z and QED-E as our basis state, so here QED-T is basically the superposition of the charge state n is equal to 1 minus n is equal to 0. This is the excited state, and QED-Z is the superposition of symmetric superposition of the charge state n is equal to 1 and n is equal to 0. Now taking QED-Z and QED-T as our basis state, we can actually write that n minus nz, when nz is equal to half, you can express it. Just to remind you once again, this can be written in the operator form, matrix form. If you write it in the matrix element form, you recall that we can write it as I here, n minus nz. We have done this kind of stuff lot many times, so it should be clear to you. And here this QED-I and QED-J, they take either QED-Z or QED-E. So if you do the analysis, then you can show, maybe we will do it in the problem solving session by explicit calculation. You can show that this number operator in the basis state QED-Z, QED-E can be written in this form: 1/2 QED-E bra Z plus QED-Z bra E. And if I take KT as 10 and KZ as 01, then I can express this number operator n minus z around nz is equal to half by this matrix 1. Actually you are going to get 0 1 1 0, and this is nothing but the so-called Pauli matrix, x component of the Pauli matrix. So I can write this as 1/2 sigma x. So we have then this interaction Hamiltonian. I can now write in terms of the Pauli matrix as this Cz by C. Now we are having a two-level system, okay? QE 0-point fluctuation of the magnetic flux, omega sigma x A plus A dagger, and we are focusing only on a single mode radiation of the microwave having frequency omega. And if I defined h bar z is equal to minus Cz by C QE 0-point fluctuation of the magnetic flux into omega, then I can write this interaction Hamiltonian in a very convenient form as h cross z. Z is the coupling parameter, as you can see. This is the coupling parameter. Z is called coupling parameter. Then in terms of this coupling parameter, I can write a very compact form of the interaction Hamiltonian, single mode interaction of the field with the Cooper pair box, two-level Cooper pair box, by this interaction Hamiltonian. This enables us to describe the whole system of Cooper pair box and the transmission line resonator through a Hamiltonian. Say we have this as our transmission line, and in this transmission line we are having a standing microwave formed it, right? So we have said this is the standing microwave, and the Cooper pair box is placed on the antinode of this microwave field. So this is this Cooper pair box. So essentially we are having a field, a single moded field. Then we have this Cooper pair box, which is a two-level atom. If we fixed ourselves around Nz is equal to 1/2, then we have the interaction term. So these are the three terms that is going to comprise the total Hamiltonian. And let me talk about the various terms in the Hamiltonian one by one. So for the field, we have the Hamiltonian, we can write for the field as the simple harmonic oscillator Hamiltonian, because the field mode acts like a harmonic oscillator. We write h cross omega A dagger A plus 1/2. Many a times, rather than writing this 1/2, we simply write it as h cross omega A dagger A, because inclusion of this 1/2 term is not going to mean anything. It's not going to change the physics if we discard it and simply write H cross omega A dagger A. And the atom, for the atom, let us consider that this energy level of the atom are basically the difference in the energy level, say kT and kg. The ground state energy is say 0 and the excited state energy is say H cross omega atom. That means the difference is H cross omega atom. Then this atom is going to be represented by this matrix H cross omega atom, that is the energy of the excited state. And then because this atom we are considering as the isolated one when we are writing the atom Hamiltonian here, so this is the matrix form of the Hamiltonian, and this actually we can write in an analytical form as well, and that would be H cross omega atom sigma z plus identity unit identity operator. So sigma z is the Pauli z component of the Pauli matrix, Pauli operator. So Pauli operator is z component of the Pauli operator is 1 0 0 minus 1. In fact, you can very clearly see that sigma z plus 1 divided by 2 is going to give you, let me actually do it. You will have 1 0 0 minus 1 plus 1 0 0 1 then divided by 2. So therefore, if you immediately see that you are going to get it as 1 0 0 0, right? And then when you are multiplying by H cross omega atom, then you are going to get this matrix form of the Hamiltonian. So our atom, two-level atom, can be written in this particular form. And for the interaction term, the Hamiltonian is already known to you. H interaction we have written earlier, and that is H cross Z sigma x A plus A dagger. So the full Hamiltonian describing the atom field interaction can be written as, from the field we have H cross omega A dagger A, and from the atom we are having H cross omega atom sigma z plus 1 by 2, and from the interaction we have H cross z sigma x A plus A dagger. So this Hamiltonian describes single mode field interaction with a two-level atom. In fact, this particular Hamiltonian is a general one which describes interaction between a field mode and a two-level atom, and this Hamiltonian is known as JC Hamiltonian, or it's called James-Cummings Hamiltonian, Cummings Hamiltonian, and this Hamiltonian is discussed also in the context of cavity quantum electrodynamics, where in cavity quantum electrodynamics a natural atom or a two-level atom is placed in a Fabry-Perot cavity, and interaction of this atom with the field mode inside the cavity is studied, and for that case also this James-Cummings Hamiltonian can be utilized. However, in our case we are going to study it in the context of superconducting qubit or superconducting two-level atom, and we are going to discuss this James-Cummings Hamiltonian in somewhat great details in the next lecture. Let me stop here for today. In this lecture we have learned about transmission line and transmission line resonator. We saw how a Cooper pair box can interact with a transmission line resonator. We have written down the Hamiltonian for a superconducting atom interacting with the microwave. In the next lecture, we are going to continue our discussion on circuit quantum electrodynamics. See you there. Thank you so much.